Welcome to the next lecture in quantitative methods in chemistry. In the previous week of lectures, we were able to see how software could be used to save your data and also could be used to do basic data analysis in terms of linear fitting, nonlinear fitting, and data analysis of similar sort. In this week of lecture, we will be trying to use more of a computation program like MATLAB. Instead of what we used last week, we ended up using a lot of spreadsheet last week, but here we will be using a software called MATLAB, where we can try to do even larger scale of data analysis. And before doing that, I felt it would be a good idea to introduce you to the syntax of MATLAB and what is the big deal about using a software of that kind. In order to do that, we will be doing simple simulations. Simulations, basically numerical simulations, where we will be taking a certain model type and trying to generate numbers and take a look at how they behave and how they look. The simplest numerical simulation that we are quite comfortable with is the straight line equation, which is y equal to mx plus c. I am sure we have seen this a lot, where the m stands for the slope, the x is the independent variable, and c is the intercept. So now if I give you a bunch of values for x, and a given value of m and c, what is going to end up happening? You can actually predict what is the value for y. Now let us say that I will give you another set of slopes and intercept, let us say m2, c2. You can once again calculate y, basically using the same equation but with different values of the slope and the intercept. One can imagine that we can have different sets of combinations of slope and the intercept, and in order to understand how does a straight line look and behave, this might be a good exercise to do, so that when we understand as the m value changes, let us say it increases, the slope of the curve increases, right? As you go from here to here, m increases. On the other hand, it could also be that the slope is negative, in which case the slope is going to have a trend that looks like this. On the other hand, in this case, if the slope is positive, it is going to have a different trend altogether. Similarly is the case with the intercept. What we are able to understand is that if the intercept is 0, it will start at 0, 0, but if the intercept is, let us say, plus c, it starts here, and if it is, let us say, minus c, it starts out here. And what you are able to realize is that for different combinations of m and c, you can generate a lot of straight lines. Why am I saying this? I am saying this because this is something that everybody can relate with, and we will start by understanding how the computation program, something like MATLAB, could help us simulate something that is a little more complicated. So we are going to take up the first example, and before doing that, we have to define a few set of syntax in MATLAB that we will end up using. Just the way we said x can be defined as a variable, let us say you want to have 0, 1, 2, 3 and as 10 different numbers. In a spreadsheet, what we will end up doing, this will be in the first row, and you can always say, let us say it is in row A2, you can always say A2 plus 1, and this will be A3 plus 1, and so on, so that these numbers can be auto generated the moment you give the first value. Same would be the case if you are trying to use a spreadsheet where you will give m in a certain cell, let us say B2, and c in something like C2. Then we can try to determine all of the y values in, say, the column of D2, where we will try to end up saying, let us say this also started from, no, let us say these two are given in B1 and C1, where the values start from A2. So the D2 will be given something like $B1, sorry, $B, $1 star A2 plus $C, $1. And then what can happen? You can generate all the 11 values for y by doing this. So similarly, what is going to end up happening, if you want to have another set of slope, you could get that slope in B2 and C2 as C2 itself in the cell C2, and then you can do something similar where you can go to E and you can define this. But remember, what you're doing is that you're doing it for two sets or a given set of slope and intercept. So of course this exercise can be repeated for a person to understand how a straight line looks, and what is going to end up happening, you have to keep on redoing all this. Instead of doing this in a laborious way, we can use computation software like MATLAB to do the same. Of course, this would also involve similar parameters such that you will have to redefine the value x, and then after you redefine, you can actually give a single or a bunch of values for m and then make it calculate. So why don't we quickly take a look on how this can be done using MATLAB. And once again, the purpose of doing this is so that you understand the syntax for MATLAB. So when you open the software in MATLAB, you have different portions that are exposed here. You are basically in a given folder which can be determined by typing the command pwd, which stands for print working directory, which is very similar to the Linux, actually same as the Linux command. And within that folder, you will be able to see the different MATLAB files that you have written. In this case, I have shown all the files up here so that you can see. This is where the editor is. Basically, when you are editing these files within MATLAB, you will be able to see them in a nice colored format so that you can understand what is a comment, what is a variable, and what is a string and all of that sort. As we just saw what all files are here and how the editor is, this is the terminal window where you type commands. For instance, we just type the command pwd. If you want to go to a certain directory, you type cd and type the name of the directory. Here is also where you will be declaring variables. Let's take a simple variable like x. Okay, let's actually not even call it x. You can call it anything. So let's call it Fred. So you can call a variable Fred, and if you give a value 2 and hit enter, then MATLAB says Fred is assigned a value 2. You can also say something like book equal to 4, then it assigns book as 4, and you can always add Fred plus book. In this case, you cannot say Fred is reading a book. Here you would say Fred plus book is 6 because Fred is assigned a value 2 and book is assigned a value 4. And here you are able to realize the simple arithmetic addition is performed between 2 and 4. You might always argue saying that, okay, why am I doing this? This can be done with a calculator. You're going to be saying that how this can be expand across a lot of numbers. The command CLC stands for the fact that you're clearing the screen, and then there's one important space that you see here which is called the workspace, and in the workspace you have all the different variables. We just defined Fred, we just defined book, and you realize what is the value assigned for Fred and what is the value assigned for book. Similarly, all different variables are also assigned. It is always a good practice to clear all the variables before we start working. So if you hit clear, you realize that in the workspace all the values are cleaned up. So once again, let's say if you want to give x as 0, then x takes the value 0 and that appears here. And in the case that we are trying to understand here, we want to generate a set of numbers for x, in which case you can say x is equal to 0, 1, 2, 3, of course with a space, which indicates that these are different elements within an array, in this case a matrix. This is 1 by 10 matrix, 1 by 11 matrix. So if you do this, x gets assigned the variable of this sort. Of course, we wanted to make our life easy, so in which case there are library functions in MATLAB which help you do that. So you can either say 1, 1 until 10, or rather 0, 1 until 10. So this is a short form notation for this, where we try to say the initial value is 0 and the final value is 10, and I would like to generate numbers with the increment of 1. You could do the same thing with the increment of 2, where you realize only 0, 2, 4, 6, 8 and 10 are generated. The same thing can be done with other parameters like linspace, where you try to say where is the starting point, where is the ending point, and total number of numbers. And if you are able to realize as you keep typing the command, MATLAB already suggests you how to use this. For instance, if you are using linspace x1, x2, that means when you say linspace 0, 10, it will generate numbers at a certain interval. And how many numbers it has generated? By default it has generated 100 numbers between 0 and 10. This is not what we want. We wanted to generate x as 1 integer units. So let us try to say x equal to linspace. As you are typing this, once again you have other recommendations that come. You also have a way where you can define what is the starting value in x1, what is the final value in x2, and how many number of digits you would like to have, which is n. So in this case we want to have 0, 10, 11. You want to have 11 numbers between 0 and 10, and if you hit enter, what you get is that x between 0 and 10 in 1 integer units. So what you have seen here is that you can generate the same 10 integer units by using different commands, and there is always an easy way of finding all this. If you go to the internet and search for how to generate numbers or how to increment a certain number, you will be easily able to find, because the online forums are fantastic. And there is one thing that we can do here is that we, instead of displaying every value that comes, if you use a semicolon, what ends up happening is that it does not display the certain values that are generated for this variable x. So now if you hit enter, you realize that these numbers are not printed, and of course the workspace has created the number here. Just for the sake of understanding, you can actually add between 0 and 20 and you generate 21 numbers. Then what you are able to see here is that x is a 1 by 21 matrix. Okay. So now that we have generated this, next thing that we would like to do is to define a certain slope. Let us define a slope of 5 units m, and we can define the intercept of, let us say, -2. So now you have defined all of this. Now what you would like to do is to calculate y, which is mx plus c. So m star x plus c. Of course, if I do not give the semicolon, it is going to print the values, and what you are able to see here is that for a given slope and an intercept with the equation that is set as mx plus c, you are able to generate the values, and you should be able to plot them very easily. So when you say plot x comma y, you beautifully get a straight line. And the most important thing here is that you do not see the number, the data that you have generated. So one way of doing this is by giving a comma with a quote O, which says that it will just show the points in here. And if you would like to join the points with a line, you can give something like this, where you are able to see these are the points that are generated, and these lines indicate direct connection between these points that have been generated. This is not a fit in by any means, so one should not confuse himself or herself with it. The advantage right now is that if you are able to change, if you would like to check how the slope for -5 works out, you can give this value back up, and of course you have to type hold on for the plot to remain, and then I can repeat y equal to mx plus c, and then I can say plot once again x comma y comma o dash, this time we will say a red color O, so that we can distinguish from what we got. And then if you take a look at the figure, what you are able to see is that the same one, but just that the slope has been changed with no change whatsoever in the intercept. Okay. So what we are able to realize in this is that with a mere change of a variable, you can generate another set of numbers. Once again, the reason for simulating something as simple as this is so that you understand how variables work and how numbers can be generated once you know a given function. Okay, now this is done. We wanted to understand how numbers can be generated when you have multiple sets of m's and c's. So let's try to do the same thing. I've already written a code here where I'll go stepwise here. So what are we doing? To start with, we are clearing all the variables, and then you're clearing the screen so that you don't end up seeing a lot of numbers that you might not want to see right now. And then you're declaring the variable x that goes between 0 and 10 with 1 integer units. Let's say between, we can actually say -10 to plus 10 with 1 integer units. We are giving a certain set of slopes, so we'll call it m1, which is 5. So we are giving m1, that is 5. We can give m2 as 6 or even -5, that's what we just simulated. And then we can give different sets of slope. So we can give c1 as, what did we give just a moment back? We gave c1 as -2. And just for the sake of simplicity, we can give c2 as also minus 2 because you want to generate with the same set of numbers. Okay, now that is done, what you have to end up doing is to say y1 is m1 star x plus c1 and y2 is m2 star x plus c2, and then you can always say plot x comma y1 with a O dash and hold on. This indicates that the figure will not change anything there, it will remain with the old set of data that you have just plotted, and then plots the next set of variable. And then you can always give an x label, y label. I have just shown you in a moment that instead of typing everything in the command line here, you can type a script out of this and then just go here and say run. When you run, what you are able to see, of course this time we have plotted between minus 10 and plus 10, we have generated x between minus 10 and plus 10, and what you are able to realize is that the intercept is exactly the same while the slopes are same in magnitude but opposite in sign, and therefore you get something like this. And also what you are able to realize is that x variable, x label and y label have also been given, where the x label here is an independent variable while y is a dependent variable on x. Okay. So the advantage of doing this right now is that we can quickly change slopes. So instead of giving a minus 2, we can also give a plus 10, and let's see how the curve looks. Now what you are able to realize is that at the value 0, while this has the blue curve has the value minus 2, while the blue curve has the value minus 2, the red one has a value plus 10. In fact, this is what you had given. For the blue you had given a intercept of minus 2, while for the red you had given an intercept of plus 10. So what you are able to realize is that you can quickly change this. But of course this is also laborious because you need to keep on defining what is your m and what is your c. So what we will see in a moment is to how to generate this quickly on the flow. So one way of doing this is that you can once again create x variable. To start with, it's better to clear any variables that you have had, otherwise MATLAB might get confused, or rather you might confuse MATLAB in the way you define. So minus 10, 1 integer units until 10, and then instead of giving slopes this way, you can give a slope which is also an array, and we can also give intercept that is an array which we have just ended up using. So far what you have seen, we are declaring the variable x, we are also declaring the variable m, and then we are declaring the intercept as variable c. Now this has been done, so let us define in this program. Once again I am restarting it by CLC, which means that I am clearing the screen and then clearing all the variables, and I am defining x between minus 10 to plus 10 with 1 degree increments, and let us try to give slope as 5 and minus 5, and then we can give intercept as minus 2 and plus 10. After having done that, we are defining a variable y which will be our final answer. Let us not worry about it right now. And then what we are trying to do, here is to loop it across the different length of m and c, meaning that now if you define m as 5 comma minus 5, and then if you ask the query what is the length of m, it says length of m is 2. For instance, let us say we define m with the 3 variables, and if you say m, it is going to find what is the length. So similar can be done for length of c. So if we are able to realize, we defined a 1 by 2 matrix, so it is saying the length is 2, meaning that it takes the larger of 1 and 2 and says its 2 is the length. So what am I trying to do here is that we are trying to loop it over. So let us once again take a simpler example. Let us define x between minus 10 and plus 10, and then we can define m as minus 5 plus 5 and minus 5. Since we have defined these two, what one could do here is that we can try to say for I, which is an incremental variable, let us say, going from 1 to the length of m. Before going that, let us ask what is length of m. Length of m is 2, so we can say for I going from 1 to length of m, give me y is equal to mi star x and So now if you say y, what you are able to realize is that y has been done 2 times probably, and then it comes up in a way where the second variable, if you realize the slope is minus phi, the values will keep reducing. So when you say plot x comma y, you will be able to see the second plot that has come up. Okay, that is a new line that has come up. It's parallel to this because we have not set a slope, which is why it passes through 0 comma 0, while in the previous case it passed through 0 comma 10, right. So now what we have realized is that although we have 2 different slopes, we are not able to simulate both. So one way of doing this is once again going from then saying y of I is equal to m of I star x, and so now if you ask what is size of y, you are able to see both has been calculated. So let's try to see whether whatever we did made sense. There you go. So you are able to plot it, but of course here the intercept is 0 for both the cases, which we are not very happy with. But what you are able to realize is that when we declare a variable x and m, you can calculate y while looping through different values of x. Unlike the last time where you had to keep on repeating writing the formula, all that you did here was to write the formula once. But remember, if you are trying to vary m and x as different values, in which case let's say if you are varying m 2 times and c 2 times, and if you want to find all combinations of this m and c, then you have to repeat the formula 4 times, but here you don't have to really do that. And you can also have varying lengths of m and c such that these can be easily generated. So now what we are trying to do here is that we are defining for the first loop as the incrementing variable I. So whenever you say for I equal to 1 colon length of m, and let's see what is the length of m. If you see the length of m is 2 in this case, what it does is that it sets I value as 1 to start with, and then goes into this portion of the code where it once again asks what is the variable of j, and to start with j is also set to 1, and it's asked what is the length of c. Length of c is also 2, so it starts with I equal to 1, j equal to 1. Then it goes here and calculates for that given value of m, which is m of I and c of j. So it can do every combination of m and every combination of c in this code. After it does that, it plots it, it keeps the graph on, and it sets it to a new variable called y, and then it goes and increments the value of I from 1 to 2 because you have the length of m is 2. Then what ends up happening? I becomes 2, and then it gets into this loop and it sets j equal to 1 and j equal to 2 and calculates all the 4. So one thing that we can do right now is that we can execute this code. Instead of typing each of the command at the terminal, I have written the code in a simple script, and when you hit run, what ends up happening? It also ends up plotting the figure for you. So what has happened here? It has plotted, of course, with different colors. We have not defined what each color is. Let's actually close this and restart this. Yeah, so what ends up happening is that for 2 different values of m, which is plus phi, which are these 2 curves which are parallel to each other, and minus phi, which are these 2 cyan and purple plot, which have a slope of minus phi. The green and the red have plus phi as the slope. And of course the intercept is different for all of these. For one side the intercept is minus 2, where the red and the cyan meet. Although they have different slopes, the intercept is same, and the green and the purple have the same intercept of 10. So what you have effectively done is that you have massively parallelized the code such that you can generate these numbers quite easily, so that you can take a look at how do these functions look. Of course we have taken a very simple example. Nothing simple will exist in science, so therefore we will slowly complicate our life. I am going to go back to make you understand how rate kinetics data can also be simulated. So let's start with something simple. We have just generated linear plots, which can be thought about as 0 order reactions. So why don't we generate some data for the first order rate plots? Once again, why are we doing this? One can always synthetically come up with data so that you can understand how to fit, and we will soon see in the next part of this lecture how simulations help you come up with informed judgments of how sampling of data can be done smartly. So that is the whole purpose of us doing this, and we are using MATLAB in this case so that you can massively parallelize or come up with numbers that can be quickly and easily generated. As always, anything that starts with a percentage in MATLAB indicates a comment. So you can always add more comments to it. Comments helps one understand what the code provides. Remember, this has to be put in by the coder. Basically, if the coder doesn't give comments, you are not going to understand what it is written for. As always, you start with clearing screen and clearing any variables that might exist. Remember, you might have defined some of the variables earlier which you don't want or might interfere with your simulation. So it is always a better idea for you to clear it up before starting. Okay, now that we have cleared the screen and cleared the variables, let's try to set the initial concentration of the chemical that you set to 1 unit. So it's always once again a good idea to give comments. So we can say units in molar. Okay, so molarity. Okay, this is because remember, whenever you are plotting concentration as a function of time, you would like to know what concentration unit exists on the y-axis. And if you might remember, for the first order reaction, A at any time t is given by A naught, where A naught is the initial concentration, times e power minus kt, where k is the reaction rate constant and t is a time variable. So similar to x variable, which is the independent variable, here time is the independent variable. Basically that's what ends up changing, and you can actually simulate the curve for different rate constants, right? So we can say with comment time variable, and this is rate constant. We can say time variable in units of seconds and rate constant in units of, this is second inverse, and rate constant in the unit of seconds inverse. Okay, so now that we have done this, we can actually plot A as a function of t and generate numbers. So why don't we run it? The moment you run, you get two beautiful curves here. And remember, what you can also see here, we can also insert legend. All right. And what you are able to see in this is that you are having data 1 that's plotted in blue, which has a rate constant of 0.5 second inverse, data that's plotted in red, which has a rate constant of 0.1 second inverse. These two, what you are able to realize is that anything that has a higher rate constant tends to decay much faster. Okay, one can always add x label, time in seconds. So now time in seconds comes up. Then you can say y label, concentration of reactants in molarity. So here you start getting this, and also you can edit the labels that you have gotten by changing k equal to 0.5 second inverse. This can also be coded in, but I am just writing it so that people who would like to use the GUI can also use it, graphical user interface can also use it. So what you are able to realize is that you are able to plot this very nicely, and you are able to also appreciate the fact anything that has a higher rate constant decays faster for the same time interval, right? All the time points that are generated are the same for both the curves, and what you are able to realize is that something with a rate constant of 0.5 falls faster than that of rate constant of 0.1. Once again, why are we doing this? We are doing this so as to understand how far or how fast can something happen, so that we appreciate which variables in the function that you are looking at make a huge difference. Okay, so now that we have done this, what we have done so far, we have been able to simulate very simple numbers with MATLAB by using linspace or other commands, and we have been able to plot a straight line by simulating a straight line, and then we have also been able to change the slope and the intercept quite a bit in different ways and do all possible combinations of slopes and intercept and plot them. And we have also done nonlinear plots, which has an exponential equation that goes here. One can also try to see whether the ln plot works out. So you can also say ln of A. So MATLAB doesn't like ln, so it's log. Log stands for natural logarithms in MATLAB. And then you have, what you have to plot is that you have to plot log of A as a function of t, so you can also plot. So we can say figure 2, plot time as a function of ln of A. So let us take a look at figure 2. So what you are able to realize, so we are not able to see the dots. So one good way of doing this, what you are able to realize is that ln as a function of t comes up beautifully as straight lines. So once again, any equation that one is able to get in any form, it's a good idea to numerically simulate it so as to understand which variables affect in a way that can be measured quantitatively. That is the whole purpose of this course, isn't it? So what you are able to realize is that this code can also be put back in. So I can write ln A. Next time this also gets done automatically. So what ends up happening, you have two figures, figure 1 that shows A as a function of t, the other one that says ln A as a function of t. So we can close this as well, and we can start adding even more details to this plot so as to make your life easy. So we can say x label time in seconds, y label A in molarity, and then you can say grid on so as to even see a grid on it, and then you can do the same thing here. So time in seconds, ln of A. Remember, ln A will have no units because log of any number does not have any units. So when you run it, you are able to see everything that goes here. And of course, you can always insert many things. You can insert the title for a given curve, for saying concentration of reactants as a function of time, first order kinetics. Right? So you are able to add a lot more things that you would like to add. So if you see here, you also have the legend that we can add, so that the legend also says how it goes. Color bar can be added. In this case, color bar doesn't make sense because we are not doing a plot that varies, which shows some contours or anything of that sort. And then you can add a line or an arrow. You can try to say at this point what is the difference that comes up, and if you are able to see the large difference that comes up between the two data points at the similar curve. So we can try to say insert arrow. So what you are able to show is also annotate and illustrate the figure. You can have a double-edged arrow on a lot of things, text box, rectangle, ellipse to say to pinpoint in a certain region what is that you are trying to see as a characteristic, and many such tools. Of course, you can also add other labels that go in. Axis which has grid lines on either side. You can have other toolboxes to zoom in, zoom out, so that you can make a plot out of it. So let's say we will zoom in there. Then what you can do is to save this as an image plot, where you can save it as a JPEG image, the first order zoom in. Okay, so it gets saved in the folder that you are trying to look for. So let's quickly check whether it did save it. What you are able to see is that the figure that we ended up generating also can be saved as a JPEG, so that this helps you understand how MATLAB can also generate the data that you have made. I mean, in this case we are simulating, but you can always have the x and y variable that comes up from the data set. If you remember the determination of critical micelle concentration for a surfactant, we had an output file from the fluorescence spectrometer which had the wavelength that varied and the intensity was the output that we got. So you can plot the intensity as a function of wavelength, and you should be able to check all these points, find the maximum for instance, and figure out which wavelength the maximum came off. So similarly to this, we can also do the second order rate kinetics. So it's always a good idea to start, since we are having the same set of variables, it's always better to start clearing the screen and clearing the variables, and running this code. I'm not going to go into the details of it. The time is once again between 0 and 10 seconds. One has to be careful here. Concentration then time in seconds, and then rate constants in appropriate units. Remember, this is a second order rate constant, so therefore it is also going to have a concentration inverse that goes in. Concentration inverse, second inverse is the kind of rate constant that you are trying to look for. So now when that goes in, you would like to generate the equation of this sort, where you would like to have y is 1 over a naught, where a naught is the initial concentration, k is the rate constant, and t is the time variable. Then you will plot t as a function of 1 over this, because remember, you want to plot concentration of reactants as a function of time. Then let's quickly go and run this. So when you are able to run it, let's take a look at the figure that we have obtained. So it's a good idea to close anything that you have opened, and then run the code. There you go. What you are able to realize is that unlike the let's insert legend first before we start talking. Okay, so let's simulate it with the same numbers that we had. We had 0.5 and 0.1. So let's simulate. What ends up happening here is that you are able to appreciate the fact that similar differences coming up, and maybe the differences for second order are even more than the first order. How are we sure to say that if you have the same initial concentration? Let's simulate all of this in the same curve. Okay, so let's try to say A is equal to A naught star exp minus k star t. It's not exp, is it? It is exp. So this is first order. Second order. Okay, and then we can say plot t as a function of a, which is what we just did, but okay, now let's run it. So what you are able to realize here, the same exact thing starts to happen. We can actually make it red so that we can distinguish. We can make it blue. Not be a bad idea to have close all here. There you go. So we know for a fact right now that this is a second order plot. First order plot, and what you are able to realize here is that anything that comes in red is the second order plot. This is for 0.1 units of rate constant, this is 0.5, and the same thing for 0.1 versus 0.5, but the blue one stands for the first order, but the red one stands for second order. Is that for any given point of time, the second order ends up having a lesser difference between the reactants at any given point of time for different orders. So once again, between 0.1 to 0.5, one can actually find the difference at any given time point and figure out what is going on. So I think there are too many points here. So let's try to simulate it with less number of points, and this is what you are able to see. And let's try to see at time point of 4. So we are trying to ask what is y, and actually we want what is 1 over y, and we want what is a. So what you are able to realize here is that this is for the set of numbers that changes as 0.5 as the rate constant, this is 0.1, and this is for second order, well this is for first order. If we see the data point, the fall for the first order is much more than for the second order, which makes no surprise because you have an exponential function, while this is a second order polynomial. And if you remember the Taylor series expansion, the second order polynomial is just a portion of the exponential function. Exponential function also has the linear, second order, third order, and all the other higher orders that come up. And what ends up happening is that as the steps go forward, the difference between the first step and second step is only about 0.17 units here, but it's about 0.34 units here, which kind of clearly indicates, or 24 units here, which clearly indicates that the first order falls much faster than that of the second order. So once again, what this helps you understand, although you would have learnt reaction kinetics for a very long time in your life, you can easily plot this to understand what differences come up for the same rate constant, of course with different units, but same magnitude of rate constant within a given time, which falls faster. Okay. Same thing can be done for zero order, but that's much more trivial to do. I leave it to you guys to perform the same. So let's go to the next problem. Then whenever you type a wrong command, it actually tries to say that function doesn't exist, and it also suggests which function we might have ended up hitting here. So if you hit enter, it helps you get the job done faster. Now I'm going to switch gears and try to say, okay, now that we have simulated different things, why don't we simulate something that might actually be something close to a real life example. And in order to do that, since it's an analytical chemistry course, I'm going to be taking up an example. The example I'm taking here is to simulate a gradient elution mixer profile. What do I mean by this? What is gradient? Gradient means as a function of time something changes. In this case, concentration of the eluent. You will see in the subsequent lectures in this series what is chromatography. In that you will be using a column, and the column will help you purify something. It will be made of column material. You will be adding a mobile phase. The solid material is the stationary phase, and then you will be adding your analyte into this and let the mobile phase help you purify the chemicals that you have prepared. Now at times the mobile phase, instead of having a constant concentration, might have a gradient concentration, meaning that, let's say if you are doing an affinity chromatography, what you would end up doing is to change the eluent concentration with respect to something. Let's say you are doing a cation exchange column, you will change the concentration of the salt as a function of time so as to elute serially different chemicals that have been bound to the column. So basically, in order to do this, you need to mix two different solutions such that the gradient elution can be done. This is commonly done in chemistry by having a setup that looks very close to this. This goes to the column. Of course, this is a very simple schematic that I am trying to draw, where there will be a magnetic stir bar. Okay. And this is the solution, let's say at 0 molar concentration, and this is the solution at 1 molar concentration. And of course, there is a pump that helps move the solution from here. So what will end up happening, since it's water and these two are connected by a chamber, connected by a tube which could exchange the liquids, what will end up happening as you keep removing liquid from here, as the volume across two of the tanks should remain same, there will be some that flows from here to here. There will be some that flows from here to here. So when that happens, what is going to end up happening? You are going to mix chemicals of two different concentrations. And what we are trying to do is to slowly ramp up the concentration of the eluent that goes into this chromatographic column slowly, such that as a function of time, the concentration of something linearly increases. Okay, so that is the whole purpose of this. So why don't we try to take an example? Of course, there are certain assumptions that go. We are assuming diffusion doesn't happen, meaning that diffusion is a passive process. If there is a concentration gradient, it will start going inside. That's why you have a pump here, meaning that the pump keeps on sucking solution from this. Of course, to start with, this will be close to the barrier and only opened when the elution is required. When such a thing is happening, when the pump is removing solution from here, solution will only move from here, and the reverse process will be less probable. And in the same case, what you are expecting is that the flow rate, meaning the rate at which it is flowing, the pump has enough pressure such that the backflow cannot happen. And it matters on both sides, because if diffusion happens on either side, this is going to get more diluted, this is going to get more concentrated. That will result in concentrations of the profile being quite different from whatever you wanted it to be. So therefore, one has to be very careful setting this up, but this has been quite very well done for many decades right now. So let's take a look. Why don't we try to simulate this? How would we simulate this? Let's think about it. Let's say there is a certain flow rate. Let's say we set the flow rate. What is the flow rate? Amount of liquid that comes out of this tube at a given unit of time. Let's say the flow rate is set to 2 ml per minute, and you are having initial concentration. Let's say this reservoir has 50 ml of of 0 molar. This also has 50 ml of 1 molar. It's quite imperative to keep the volume constant, because if the volumes are in constant, water is going to flow from one to the other, and if you especially have unequal volumes, the flow is going to be quite different, although you have a pump here. So it's always advised to have the same volume so as to achieve this. So when this is going to end up happening, when you open this up with this given flow rate, slowly solution is going to move in. So the variable that we get to alter is the flow rate, and we can simulate assuming that when you take 2 ml out of this, meaning that when it goes from 50 to 48, this is not the way in reality it works. If you take 0.1 ml, it's going to also get equilibrated from the other tank, but for simulation purposes, we can take a step that is equal to the flow rate, and when that happens, instantaneously 2 ml flows from here to here. The dilution happens. How does the dilution happen? We can use the equation V1 M1 equal to V2 M2, and of course this is not a straightforward equation because you have a certain volume here. So we can say this is tank B and this is tank A. So you have a certain volume B, you have a certain concentration in B, and certain amount of volume comes from A. So we can say volume A prime times concentration of A, right? So divided by total volume of VB plus VA prime. Remember, when 2 ml flow rate happens, when it goes from 50 to 48, 1 ml in this simulation will flow from here to here so as to keep the volumes 49 and 49 ml respectively, because water will always try to be in the equal level. So by doing this simulation, one can try to understand how long or how much can be done. So that is what we are going to be simulating. It's a very simple first order simulation. So let me open the gradient elute simulation. And if you realize, this is a simulation that is written with a lot of inputs here or information as comments. So you'll always start with a close also as to close any figures that might have been opened. Clear, CLC clear cleans up any variable in the workspace, and CLC ends up cleaning anything in the terminal. And if you see here, the assumptions are also written, and you are able to see a section where initial conditions are set up. I'm putting the initial volume to 50, volume in ml, and then the concentration we agreed is 1 molar. So we can write it in millimolar, so we can say 1000 millimolar, and then concentration in B. This is the reservoir where from which the solution goes into the column, and then of course we are setting the initial volume in both of the reservoirs within a given variable initial volume, and flow rate per minute, which is short formed as FRM, is given as 2. In this case, it's 2 ml per minute, and then I'm calculating the number of steps. If you are able to realize, if you have 100 ml of total solution, 50 ml in reservoir A and 50 in B, about 100 ml has to be eluted out. If 100 ml has to be eluted out, what ends up happening is that if you are having 2 ml flow rate, you are going to run the entire flow for about 100 ml by 2 ml per minute. That's going to be 50 minutes that comes up. So I'm just calculating it. I'm just trying to say the initial concentration of the eluent is 0 molar. Concentration of eluent in molarity. Then similar way that we did last time, we are calculating the number of increment steps such that number of steps, in this case we will be having 2 ml flow rate, 100 ml is going to go, we are going to calculate in 50 number of steps, and then all I am doing here is carefully doing each step that I just mentioned. The first step here is to change the volume from reservoir B, where I say volume in reservoir B. In the next step is going to be the volume that was there previously minus the flow rate, meaning that if you started from 50 ml, if you are having 2 ml per minute, and if you are assuming that's the quantum that you are trying to simulate, if you take 2 ml out of 50 ml, it's going to be 48 ml. And after having done that, you should also calculate the amount of volume that will come up from A into B. And how we are calculating this, the volume in reservoir A after the change is going to be the initial volume, in this case it will be 50, and the volume that you have just calculated, which is 48, and that divided by 2. So you're going to have 50 plus 48 by 2, which is going to be 49. I'm just doing it for the first point so that I can understand better. Now what is going to happen? You're going to have 48 ml in reservoir B and 49 ml in reservoir A. So basically 1 ml is going to flow in. If you take a little bit of time, where the comment also gives here how the equation is calculated, you will understand. If you set the concentration of B in the next step has to be volume in B, VB times MB, plus volume A minus volume B, basically 49 minus 48, how much flows in, times half of it, time concentration of A, divided by the total volume that you have calculated in A. So basically this is the formula that I just wrote here in a very quick fashion. Basically you want to understand how much is in volume in B, what is the concentration in B, how much volume flows from A and what is the concentration of A, and then the total volume that ends up coming, which is after equilibration, it's 49 ml. After having done that, you want to increment the volume, so 1 ml gets added in volume in the reservoir B, so 48 becomes 49, and then you are calculating the concentration of the eluent, and then the next step that you are doing is to plot it. So why don't we quickly run this simulation? So what you are able to realize is that the concentration that comes out of the elution, assuming no diffusion and all the other assumptions that have gone in, as a function of time, if you are able to realize it goes from 0 to 50 minutes, let me make this a little bigger, it goes from 0 minutes to 50 minutes, and in the elution time, you nicely have a linear gradient that comes out of it, right? So what you are able to realize is that any setup that you might end up doing, you would be able to simulate things in a nice fashion so as to ensure that whatever you are thinking is what transpires when you are actually making the setup. Okay, so simulations are an extremely wonderful tool for one person to understand how is the system going to behave, provided you already have a model that exists. For instance, if you are trying to talk about how free energy changes as a function of temperature, one can easily plot it, right? If you know the equilibrium constant as a function of temperature, you could actually calculate what is the delta G naught, because it's given by delta G naught is minus RT ln of K. You know the value of K, you know the value of capital T, you should be able to do this, right? In the next lecture that we will be seeing, we will be trying to understand how to simulate such rate kinetics. I will be taking Michaelis-Menten rate kinetics for that as an example, so that we understand how this works out. Thank you.